Fortinet is having a really hard time this week when it comes to their FortiWeb application. In this video, we're talking about two CVEs that just came out, and they're both pretty crazy. If you're not aware, FortiWeb is this web application firewall, or a WAF. Basically, what you do with a web application firewall is you park this piece of software in between the internet and your web application, right? What it does is it acts as a filter that looks at all of the traffic that comes in and tries to see if anything weird is happening in the traffic that's interacting with your web application, right? So kind of this Venn diagram of the things that it can pick up, right? You have normal application traffic, which is your buddy Mark Smith using your application. And then on the right, you have Janet over here. Poor little Janet mistyped her name. So you see that it detects that as a potential anomaly. And then you have this other guy over here he is using the traditional SQL injection, right? So, by putting this in between your application and the internet, you get a good hint as to when bad things are happening. Now, the reason I'm making this video is I scroll r/cybersecurity pretty regularly. And I saw this person saying that they have a bunch of FortiWeb honeypots, like basically fake instances of the application around the internet, and they were getting some hits off of this request here, right? And you'll see there's kind of basically, a cookie that has some content in it and some fake payloads, test. So I did some diving and I found this really, really good write-up here by a guy named poner.gg. I'll put the link to his blog down below. And apparently this is a bug that I'm not sure if he discovered the bug or if he just wrote up a technical write-up on the bug. It says it was assigned to this CVE, so I'm assuming it's their bug, right? But basically, it's a really, really interesting bug that because of an out-of-bounds read in a field in a cookie, you're able to determine ahead of time what the key is to validate a session cookie. There's a lot of words going on there. If you're new to cybersecurity or a lot of those words don't make any sense, I will happily break them down, right? So basically, when you authenticate to the FortiWeb application, you're given this authentication cookie, right? So you have some content here that doesn't do anything, but you have kind of these three fields. You have era, you have payload, and then you have this other one called auth hash, right? And here the guy poner.gg kind of breaks them down. This is your traditional verification or authentication of data using a thing known as an HMAC, right? So the payload is the data, right? This is going to contain the thing that you're trying to tell the web server that is true. So in a web application scenario, you're trying to tell the application who you are, so your username and your role. Like maybe I'm an admin, maybe I'm a contributor. I have some properties about the session that I was authenticated. But the problem is if I have this payload, right, I shouldn't just trust the payload as the firewall, right? I should have some way of authenticating who says that is true, right? I want to verify that I, the firewall, say that it's true. And the way you do this most of the time is with this thing known as an HMAC. An HMAC is a message authentication code, and the H stands for hashing. It uses hashes. And the way it works is you have typically the data you're trying to authenticate, and you have a key. And by doing a series of hashes of the key and the data together, it is only possible you can create that HMAC if you know the key and the data. So to do this kind of authentication, you take the thing you're trying to authenticate and the HMAC of that thing with the key, and you present that to the server, and then the server calculates the HMAC of that contents and says if the HMAC that it calculates matches the HMAC presented, that means that you both use the same key, which means you're both the same person or you both have access to the same data. You're at the same level, right? Now, the question then becomes, right, where is this key derived from? That's where this weird era value comes from. What I think era means is era is what variant of the cookies are we using? Maybe in one era they use DES3 or 3DES, and then in another era maybe they use AES, right? And this era kind of determines, okay, what key are we using? And so in the disassembly here, if you guys aren't in the world of reverse engineering, what this is this is IDA Pro. Okay, this is IDA taking the assembly code of the binary that runs on the firewall, right? The HTTPD binary. And the assembly is machine readable, and it's lifting it up to a pseudo C, a fake C implementation of what it thinks the C looked like from the developer. And that's why all these variables have really terrible names, right? You have V27 or V2. These are the fake names that IDA gives to variables that it sees because it does not have the human intent behind those variables, right? And you will see that the person doing the reverse engineering has renamed some of the variables themselves, right? You have like n and auth hash here. Because the symbols in this binary, right, like the names of functions don't go away, like EVP decode update, you can use the signature of that function to kind of like infer what this means. You can go to the signature of the EVP decode update function, right? And because the functions like have variables with names, you can use those named variables to reverse engineer from what you're seeing in the disassembly, what is going on, right? And so through that, they found out that basically the key used to validate the HMAC, right? Again, the hash-based message authentication code is pulled from this heap variable called cookie FWeb secret keys, right? And that's an array, right? It's an array of keys. And what does it use to index into the array? Well, because there are multiple potential varieties of keying going on, it uses the era value to act as an index into those keys. Hold on a minute, but what if they don't validate the value that is being used as an index? And this is what they say here in a little comment. This is the reverse engineered, like basically making notes to themselves about the bug. Is this an out of bounds read by the era value? And what they'll show you here is that this is the memory contents of the firewall while it's running. And these are the two different keys available basically if you use era value 0 or era value 1, right? But what if we use an era value of 12, right? Because it's not validated, we're able to bring the index that pulls the key into memory to do that HMAC to a value that we know, which is just going to be all zeros. And because we now know the key that is used to do the encryption of the payload as well as the HMAC, they are able to forge their own cookie that says, oh, hey, by the way, I'm admin, I have admin privileges, and I'm able to do whatever I want all the time, right? So that's a really cool bug, and here they show themselves using a little Python script they wrote to basically get a magic value from the server, forge a fake cookie, and then use that to view an authenticated API in the firewall, which is pretty freaking sweet. There is this one little note they made that basically for this to work, you have to have the user has to be active for the session to run. So like it's not as cool as like just a pure remote RCE, and there is a little bit of brute force that has to happen. But as I mentioned, no higher than 30. The bug the field that you're brute forcing apparently is refresh total logins. I think what's happening here is it's an integer within the session information that says how many times has that cookie been refreshed, right? Sometimes with like web applications, you have to do refresh tokens that allow you to use the same cookie without changing your session, right? Without making a new session. So maybe this is like how many times has that session cookie been refreshed. So yeah, pretty neat bug. One way that the developers could have caught this bug, by the way, is with a neat little tool called ASan. If you guys aren't aware of like how all applications work, at the end of the day, right, that web application was being ran on a device, and that device is somewhere running C. And as we saw kind of in the reverse engineering here, this is the breakdown of a C application that is binary and the device, and they're lifting it up to the pseudo C. And so I wrote up a little example of like how we can possibly have detected this using fuzzing or some kind of like automatic testing. This is a very simplified version of the application. Obviously, basically I just have an array of two strings, a magic zero value that we don't want to be able to choose, and then we have us basically giving the program an index and then using that index to index into an array. Now obviously there's a huge bug here because I am not validating that I is 0, 1, or that's it, 0 or 1. If it's any higher or lower, it's an out of bounds read, but because C is the way it is, there's no real way for me to like automatically check that at runtime, right? So we make this program here, bada bing, bada boom, and you'll see that I can easily read outside of the index, and this one crashed. I'm not sure why that one crashed. Oh. And because I can just put whatever value that I want here, it's going to let me do basically whatever I want. So like nothing too surprising there. One way that this could have been caught is by using this tool called Clang. Clang is a compiler within the LLVM framework, and that framework has a bunch of sanitizers. Sanitizers are basically these tools you can add to your code that at runtime, it makes this huge performance hit, right? It makes your code, I think, like 50% slower. But what it does is it installs all of these guardrails inside of your code that you can detect if there are out of bounds reads, out of bounds writes, buffer overflows, etc. Very good for testing your code, for fuzzing your code. And so when we compile this code with fsanitize address, what we're able to do is run the code, and if I run the code with 2, right, I index outside of that array, I will get a crash and says, hey, by the way, address sanitizer found that you did a global buffer overflow or an out of bounds read, and you're trying to read this magical shadow data that you should not be able to read, right? And it gives you a whole breakdown of what happened and exactly in your code where it is. So in my opinion, right, what a company should be doing is, especially in code that is like authentication, that is forward facing, take this function here that looks like the primary driver of the authentication, throw a little bit of fuzzing at it, right? Compile this with ASan, and if you do that, you'll probably quickly see that, error, this value here, is not guarded by any kind of validation of the inputs. And there's a second bug also in FortiWeb from about a month ago that, again, it's like, I'm not trying to shit on FortiWeb, I just find some of these bugs, like this one's pretty cool, right? This is a bug that you can out of bounds read to determine key values ahead of time and then use that to forward signatures. That's cool. This one's just funny, right? So this bug is basically, there's an application path inside the HTTP daemon that goes to a certain handler, and to access that handler, you have to have a valid bearer token that is issued to you by the application firewall, right? Very traditional authentication stuff. You give them a bearer token, you use that token to do stuff on the firewall. And so when you make this request, it's first checking your access. It does fabric access check, and it reads in your 128 byte string into some buffer, and then calls get fabric user by token. So it's going to look up in a database based on the token you've provided what users have that token. And if you can't predict what user has that token, then you're crap out of luck, right? Well, what if I told you that they just do this little thing here? I'm gonna move my fat head out of the way. Does anybody see an issue with this? Anybody in the chat see this? Yeah, so traditional, SQL injection, nothing too fancy to talk about there. It's just kind of funny that, even in a web application firewall itself, where the purpose of the device is to prevent SQL injections, like they even in the example here use an SQL injection as like their look what we detect symbol or look what we detect example. The device itself is vulnerable to an SQL injection. And again, I'm not doing this to shit on anybody. I'm not doing this to like make fun of anybody. I think it's just important to highlight that like code is so easy to make like single mistakes in, like a single mistake like this. For example, you simply forgot to validate one piece of user data. Oh my God, but that user data is just a number. Who cares? Well, that number eventually turns into an index, that turns into a read, that turns into a key, that turns into authentication, right? So it's just kind of crazy. And then this one's a little more egregious. Like I'm not going to say too much on this, but come on guys, they're not parameterizing their SQL query. What they should be doing is like where token equals question mark is like the query, right? And then I don't know what SQL engine they're using. Maybe it's like MySQL under the hood. We'll have a function that says like, run query, and as variable arguments, it will take the arguments that need to go into that parameter, into that query, and it will properly sanitize and parameterize them such that you don't have to handle it yourself. Because all you have to do here is put a little, 1, 2, 3 or blank equals blank, and then you're in. And how they turn this into RCE is pretty cool. Basically, the underlying SQL engine, you're allowed to write into files. Oh yeah, it looks like it is MySQL, and it's because it's root. You can just write the contents of the query into a file. And so what they did is they used that query to overwrite the matplotlib library that lives on the device. So every time the Python engine comes to life to do any kind of data analysis, it runs their code, and they can use that to get RCE on the device. So pretty neat. To answer your question, would Rust have fixed this? Yes, Rust would have fixed this bug, the out of bounds read in error, but would it have fixed the SQL injection? No, it would not. That being said, obviously writing a code base in Rust has its own issues. You need to make sure the entire organization is going in that direction, and if they're not, it's kind of a fruitless effort. But that being said, I hope you enjoyed this video. If you did, give me a little kiss right here on the cheek, and we'll see you in the next one. Take care.